Behold the sun, big, bright, and hot. It's the crux that this planet's survivability is built on, and the creatures of Earth revel in it, even to the point of worship. Life without it was unimaginable, until 1977, that is. When a team of scientists photographed the Galapagos Ridge 8,000 feet below the surface, they found a booming community on the ocean floor, thriving in perpetual night. These scientists discovered what would become known as a hydrothermal vent. Hydrothermal vents are hotspots on the ocean floor where the Earth's surface is cracked, which usually happens when two tectonic plates spread apart. Seawater rushes into these cracks, where it percolates underneath the ocean floor and becomes superheated by the Earth's mantle. It gets so hot that it picks up metals and minerals, like iron sulfide, barite, and more from the crust, and eventually becomes buoyant, shooting the water back out through the vent at temperatures up to 405 degrees Celsius. When this water makes contact with the cooler surrounding water, the minerals precipitate out, forming magnificent ore structures known as vent chimneys that can stretch up to 60 meters. But these chimneys do more than give the bottom of the ocean a Gothic aesthetic. They serve as a foundation for a bustling city of alien-like creatures. The biggest star of these communities is, arguably, the hardest to see: chemosynthetic bacteria. Unlike many primary producers, who get their energy through photosynthesis, the bacteria that live in hydrothermal vents survive through chemosynthesis. When mineral-rich water is flowing out of a vent, it also contains gases toxic to most organisms, like hydrogen sulfide or methane. Chemosynthetic bacteria turn the chemical bonds in these gases and fix it into energy. They're so successful in this harsh environment that they can accumulate in thick layers, forming microbial mats. But they don't just accumulate near the vents. They'll settle right on their neighbors. Take the Yeti crab. What these crustaceans lack in pigment, they make up for in style, with hundreds of blonde, hair-like structures covering its body. These are called setae, and they are what allows these crabs to make a meal with the wave of a wand. Or the wave of an arm, actually. Bacteria like to settle on the setae, and when the crab swings its arm, it mixes up the water column and whisks the bacteria off, creating a slurry of food for the crab to eat. But for a smaller snack, they'll just pick the bacteria off. Another star of the hydrothermal vent is the tube worm. Living in clusters with their bright red plumes atop stark white chitin, they're pretty hard to miss. They also use chemosynthetic bacteria as a food source, but in a remarkable way. When larval tube worms become juveniles, they stop floating in the water and attach to the substrate, where bacteria can enter through its skin and live within the tube worm throughout its life cycle. In exchange for a safe place to live, the bacteria will feed the tube worm internally. This happens through the worm's plume, which can take up chemical compounds in the water and deliver it to the bacteria to be turned into energy. Bivalves and mussels, who harbor chemosynthetic bacteria in their gills, also live through this symbiosis with the microbes. It's these primary consumers, along with other annelids, mollusks, and arthropods, feeding off the bacteria that give rise to bigger carnivores, like octopuses and ratfish, to make a well-rounded, diverse food web that we have just begun to explore in the last few decades. The far-removed nature of these communities that kept them a secret for so long could give us a reason to think that they're out of harm's way. If they were so inaccessible to us up until the 1970s, then what real dangers could these organisms, who are already thriving near noxious gases and in super hot water, really face? Well, as it turns out, human impact may be able to reach this deep. Even though the animals near the vents can obviously thrive in hot water, they wouldn't necessarily thrive if all the water in the ocean warmed up too much. As the ocean warms, it holds less oxygen and also becomes more stratified. This could result in an overall oxygen reduction, affecting behavior, physiology, reproduction, and more. This reduced circulation that occurs as a result of warming waters affects life in shallow waters too. Over thousands of years, nutrients picked up by the hot water from the vent is welled up to the surface, feeding into huge blooms of phytoplankton, which serve as an invaluable food source to primary consumers in other parts of the ocean. A more direct effect that these habitats could face in the near future is mining. As mentioned previously, the superheated water that spews from a vent picks up minerals and metals where they precipitate out and accumulate nearby. Some of these metals are precious and useful, like gold, silver, zinc, and copper. This is of much interest to industries around the world, and the International Seabed Authority is projected to begin giving licenses to organizations for the purpose of the commercial mining of these ores in early 2020. While it's difficult to predict the exact effect this would have since it's never been done before, it could potentially be a significant blow to hydrothermal vent communities. The presence of a 300-ton vehicle needed for seabed mining and the disturbance of the substrate alone could be detrimental. Furthermore, the dredging up of metals and exposing them when they wouldn't normally oxidize could be toxic to the ecosystem, and would be further exacerbated as the ores are transported from the seabed to the surface, bringing a massive sediment plume with it. Other stressors that could come with mining include anthropogenic light and noise. The constant light and noise that would come with mining, in a world that has always been dark and quiet, could have serious behavioral and physiological effects on deep-sea organisms, such as disorientation, masking methods of communication, affecting migration for mobile species, and more. And there's more than one reason to choose these communities over precious metals. It's accepted that active hydrothermal vents most likely showed up shortly after the presence of liquid water on Earth over 4 billion years ago, meaning that they could potentially serve as a time warp back to the days of primordial soup. By comparing the more archaic physiologies of hydrothermal vent organisms to their more modern relatives, we can get a better idea of what the earliest life forms on the planet were like and the chemistry that allowed life to happen in the first place. On the other side of the spectrum, these habitats don't just give us insight on our origins, but perhaps our future as well. The large quantities of metals and toxic chemicals, high temperatures, and low pH due to sulfites make hydrothermal vents a decent template for what life may be like down the road as the climate of our Earth changes, and studying the organisms who thrive like this could help us understand ways life elsewhere can cope with that. Hydrothermal vents can be useful in medicine too. Studies show that the high metal content near hydrothermal vents contribute to the synthesis of antibiotics that are completely new to us humans. As we become more resistant to the antibiotics we currently use, the ability to study these novel strains becomes more and more valuable. And then there's the inherent value that lies in the corners of the world that are tucked away. Hydrothermal vents are hotspots of biodiversity, filled with remarkable creatures, some of which we haven't even met yet.